Hello. In this final video of this unit, I'd like to talk about how free energy is related to pressure, equilibrium, and work. Let's begin with the question. In a gas phase reaction, how does the free energy of the system, G, depend upon the pressure? Well, our definition of free energy, G, is that it's equal to the enthalpy, H, minus the product of the temperature and the entropy, S. The enthalpy of a system does not depend upon the pressure, but the entropy of a system does depend upon pressure. So if we consider 1 mole of an ideal gas at constant temperature, we ask ourselves which has greater entropy, 1 liter or 10 liters. Obviously, 10 liters, because at a larger volume, there is greater positional probability, more ways to arrange the particles, so therefore a larger entropy. Okay? Correspondingly, that means that there is a lower entropy, the entropy at low pressure is greater than the entropy at higher pressure, or as the pressure of a system increases, the entropy decreases, and therefore, according to the equation above, the free energy should increase as well. Okay? All of this leads to a derivation that our textbook completely skips over because it's beyond the scope of the course, that tells us that the free energy of a system at non-standard pressure is equal to the standard free energy, G naught, plus RT times the natural log of the pressure, where R is the gas constant in units of kilojoules per mole Kelvin. G naught is the standard free energy of the system at a pressure of 1 atmosphere. So when the pressure is 1 atmosphere, the natural log of pressure is 0, and the free energy is equal to the standard free energy, G naught. So how does the free energy change, delta G for a reaction, depend upon the pressure? Well, the free energy change is the sum of the free energies of the products minus the sum of the free energies of the reactants multiplied by their stoichiometric coefficients. So if I consider a hypothetical reaction in which little a moles of big A in the gas phase react to form little b moles of big B in the gas phase, delta G is B times the free energy of B minus A times the free energy of A, where the free energy of each component is simply equal to the standard free energy plus RT times the natural log of the partial pressure of that component. Okay? We will plug those in, collect terms, blah, blah, blah. I will spare you the ugly algebra, and what it all comes down to is delta G equals delta G naught plus RT times the natural log of the partial pressure of B to the B power divided by the partial pressure of A to the A power, which you see very clearly is simply equal to Q. So that gives us the expression delta G is equal to delta G naught plus RT ln Q, or the free energy change under non-standard conditions, delta G, is equal to the standard free energy change, delta G naught, plus RT ln Q. What do these terms mean? Delta G naught is the free energy change for the reaction when all reactants and products are at a pressure of 1 atmosphere, whereas delta G is the free energy change for reaction when the products are at specified or non-standard pressures. So let's use this equation to calculate delta G for a reaction under conditions of specified pressure. So here we have hydrogen sulfide gas reacting with sulfur dioxide gas, forming rhombic sulfur and water vapor. And we are given a system which has the following partial pressures. And the question is, what is delta G for this particular system? Well, we know that to calculate delta G, we have to use delta G equals delta G naught plus RT ln Q. That tells us we need two quantities. We need to calculate delta G naught, and we need to calculate Q based on the information that's given. Delta G naught we know how to do, and because we are at 298 Kelvin, that makes our lives a little bit easier. Of the three methods of calculating delta G naught we learned in the previous video, let's use the one that uses standard free energies of formation. So delta G naught is equal to 2 times the standard free energy of formation of water vapor plus, minus 2 times the standard free energy of formation of hydrogen sulfide minus the standard free energy of formation of sulfur dioxide. I left out the standard free energy of rhombic sulfur because that is the element in its standard state. Plugging those in, I get 2 times negative 229 kilojoules per mole minus 2 times negative 34 kilojoules per mole minus negative 300 kilojoules per mole, or delta G naught equals negative 90 kilojoules per mole. So under standard conditions, this reaction is spontaneous because it has a negative value of delta G naught. Now, to calculate Q, the reaction quotient for this reaction, I'm going to write out the Q expression. Q is equal to the partial pressure of water vapor squared divided by the partial pressure of hydrogen sulfide squared times the partial pressure of sulfur dioxide. And I will plug in the values that are given in the problem. This is equal to 3.0 times 10 to the negative second squared over 1.0 times 10 to the negative fourth squared times 1.0 times 10 to the negative second, or a value of 900 for Q, the reaction quotient. So now I can plug into the equation. I'll write it down again for reference. Delta G equals delta G naught plus RT times the natural log of Q. This is equal to negative 90 kilojoules per mole plus R is 8.3145 times 10 to the negative third kilojoules per mole Kelvin times our temperature of 298 Kelvin times the natural log of Q, 900. Let's just look at what these terms are. So this is negative 90 kilojoules per mole plus an additional 17 kilojoules per mole, or delta G is equal to, not delta G naught, but delta G is equal to negative 73 kilojoules per mole. So the standard free energy change for this reaction, that is delta G under standard conditions, is negative 90 kilojoules per mole, but delta G under these specified non-standard conditions is only negative 73 kilojoules per mole. So what does that mean? Well, the fact that delta G is negative means that under these specified conditions, with the partial pressure stated, the reaction is going to proceed spontaneously in the forward direction to achieve equilibrium. A negative value of delta G means that under these conditions, the forward direction is spontaneous. Okay? If delta G is positive, then that means reaction in the forward direction is non-spontaneous. In contrast, it would proceed spontaneously in the reverse direction to achieve equilibrium. That's the significance of the sign of delta G we calculated. What is the significance of the magnitude? Negative 73 kilojoules per mole can be thought of as the driving force that is pushing the reaction towards equilibrium. Remember, free energy was originally called available energy because it's the energy that is available to do useful work. So under these particular conditions, the partial pressures that were specified, there are 73 kilojoules per mole of reaction available to push the reaction towards equilibrium, and in doing so, to do useful work. So now, let's talk about free energy and equilibrium. What is the relationship between these two quantities? Well, we just said that delta G is equal to the standard free energy change plus RT ln Q. As a reaction under specified conditions approaches equilibrium, as we know, Q approaches K. As a reaction proceeds spontaneously in the direction that will achieve equilibrium, the numerical value of Q approaches K. But if we consider the free energy of the system, delta G, or the free energy change, to be the driving force pushing the reaction towards equilibrium, as it approaches equilibrium, delta G gets smaller and smaller and eventually approaches zero. The closer you get to equilibrium, the less of a driving force there is pushing you towards equilibrium. At equilibrium, Q is equal to K, and delta G is equal to 0. That's important. There is no longer any thermodynamic driving force pushing you towards equilibrium because you're there. So let's plug these back in. Delta G now is equal to 0 at equilibrium, is equal to delta G naught plus RT ln K because Q became K. Or rearranging, delta G naught equals negative RT ln K, or in the exponential version, K equals negative delta G naught over RT. These two horrendously useful equations tell us exactly how the equilibrium constant K is related to delta G naught, the standard free energy change for reaction at a given temperature. So, if the standard free energy change delta G naught is negative, then the natural log of the equilibrium constant is greater than 0 and k is greater than 1. Makes perfect sense. We said a negative value of delta G naught is associated with a spontaneous process, and for a spontaneous process, the equilibrium constant is greater than 1. If delta G naught happens to be equal to 0, then the natural logarithm of k is equal to 0, and the equilibrium constant is equal to 1, meaning neither the reactants nor products are favored. On the other hand, if delta G naught is positive, then the natural logarithm of the equilibrium constant is negative and k is less than 1. Again, a positive value of delta G naught is associated with a non-spontaneous process, and that is consistent with an equilibrium constant that is less than 1. So now it all makes sense. So, how exactly does the equilibrium constant depend upon temperature? Well, you might be tempted to say, oh, there it is right there. K equals e to the negative delta G naught over RT. But remember, delta G naught is a function of temperature as well. Okay, so we have to take that into consideration. Delta G naught equals negative RT ln K, but delta G naught is equal to is equal to delta H naught minus T delta S naught. There it is. There's the temperature dependence of delta G naught. So let us set these two terms equal to each other. If they're both equal to delta G naught, they're equal to each other. And that gives us negative RT ln K equals delta H naught minus T delta S naught. Or rearranged to isolate ln K, we have ln K is equal to negative delta H naught over RT plus delta S naught over R. Here now is the most useful equation of this unit. And that is because if you know the standard enthalpy change and the standard entropy change for a reaction, which we know how to calculate easily given the thermodynamic tables, we can calculate the equilibrium constant at any temperature, or the temperature at which the equilibrium constant has a specified value. And that is tremendously useful. So let's do a problem in which we calculate the standard enthalpy change, the standard free energy change, and the standard entropy change for a reaction, and the equilibrium constant at this particular temperature. So we look at the equation, which involves reaction of 1 mole of hydrogen and 1 mole of chlorine to form 2 moles of hydrogen chloride gas, and we easily see that this reaction is the formation of 2 moles of hydrogen chloride gas from its elements in their standard states. Therefore, delta H naught, the standard enthalpy change, will simply be equal to 2 times the standard enthalpy of formation of HCl, which we can simply look up on the thermodynamic tables. That's 2 times negative 92 kilojoules per mole, or negative 184 kilojoules per mole as my standard enthalpy change. For the standard entropy change, we will have to use the standard entropies listed. So this will be 2 times the standard entropy of hydrogen chloride gas minus the standard entropy of hydrogen gas minus the standard entropy of chlorine gas. That's 2 times 187 joules per mole Kelvin minus 131 joules per mole Kelvin minus 223 joules per mole Kelvin is equal to plus 20 joules per mole Kelvin. Okay? The reaction has a slightly positive standard entropy change because hydrogen chloride has greater entropy than either H2 or Cl2. Now, to calculate delta G naught, the standard free energy change, I could use either the standard free energies of formation because we were 298 Kelvin, or I could use delta H naught and delta S naught. Either method will give you the same result. So for simplicity, I'm going to use delta G naught equals delta H naught minus T delta S naught because we just calculated those. So this will be equal to negative 184 kilojoules per mole minus the temperature of 298 Kelvin times delta S naught converted from joules per mole Kelvin to kilojoules per mole Kelvin, so our units work out consistently. And that gives me a value of delta G naught of negative 190 kilojoules per mole. Okay, so this reaction has a negative enthalpy change, it's exothermic. It has a positive entropy change, and therefore it must have a negative standard free energy change. It is spontaneous at all temperatures. Now to calculate K, because we calculated delta G naught at 298 Kelvin, notice that temperature was involved here, so this is at 298 Kelvin. Delta G naught is a function of T. We can simply do K equals e to the negative delta G naught over RT is equal to e to the negative 190 kilojoules per mole divided by the product of the gas constant, 8.3145 times 10 to the negative third kilojoules per mole Kelvin times my temperature of 298 Kelvin. That's going to give me a positive exponent, and in fact that's e to the 76.68 if I evaluate the exponential term, which gives me a value of 2.0 times 10 to the 33rd as my equilibrium constant. And that makes sense. A large negative value of delta G naught, the standard free energy change, tells me it's a very spontaneous reaction, and that is consistent with a very, very large value of K. Now, let's ask the question, if I place the three components of this system in a flask at a pressure of 1 atmosphere each, in which direction will the system shift to reach equilibrium at 298 Kelvin? Now, there are two ways to answer this question, and either one works. Pick the one that's easier. The first method would be to use Q, and the second method would be, and of course if we use Q then we compare to K, the second method would be given these conditions, calculate delta G and use the sign of delta G to determine whether it's spontaneous in the forward or reverse directions. We will do both of these to illustrate that they both work. So for method number one, I will simply calculate Q as the square of the partial pressure of hydrogen chloride gas divided by the partial pressure of hydrogen gas times the partial pressure of chlorine gas, which is equal to 1 atmosphere squared over 1 atmosphere times 1 atmosphere. And if you get out your calculator to do this, I'm going to fail you in this class, so please don't. So this gives us 1. How does 1 compare to K? Well, we just said K was really, really big. This is much less than K. If Q is less than K, that must mean we have to shift to products or in the forward direction in order to achieve equilibrium. The other way we could do this is to calculate delta G. Delta G equals delta G naught plus RT ln Q. And whatever my conditions of partial pressure were, I would simply plug them into the Q expression. I would plug in the delta G naught that I calculated and calculate a value of delta G. And if delta G is negative, that means it would be spontaneous in the forward direction. If delta G is positive, that means it's spontaneous in the reverse direction. In this particular case, because Q is equal to 1, the natural log of Q is simply equal to 0, so this whole term goes to 0. That tells me delta G is equal to delta G naught is equal to negative 190 kilojoules per mole. And because that is less than 0, we predict the same, which is that in order to achieve equilibrium, this set of conditions would have to shift towards the products. So again, use either of these two methods to calculate whether a given system must shift towards the products or reactants to achieve equilibrium. You will get the same result. Now, one more problem. The combustion of nitrogen monoxide to form NO2 is represented by the following equation. We'll calculate the standard enthalpy change, the standard entropy change, and the standard free energy change, and K at 298 Kelvin. So, delta H naught, I'm going to use the standard enthalpies information. I'm going to just jump to the chase. I know I told you not to do this, but for simplicity, I'm going to do this. 2 times the standard enthalpy information of nitrogen dioxide minus 2 times the standard enthalpy information of nitrogen monoxide is negative 112 kilojoules per mole. The standard entropy change is 2 times the standard entropy of nitrogen dioxide minus 2 times the standard entropy of NO minus the standard entropy of O2 gas is negative 147 joules per mole K. And I'll calculate the standard free energy change using delta H naught minus T delta S naught equals negative 127 kilojoules per mole minus the temperature 298 Kelvin times negative 0.147 kilojoules per mole Kelvin equals negative 68 kilojoules per mole. So here is my standard enthalpy change, here is my standard entropy change, and here is my standard free energy change for this reaction at 298. At 298 Kelvin, it is spontaneous, and I can calculate K using e to the negative delta G naught over RT. With your permission, I will skip over plugging these things in just to save space, but I'll do it exactly as we did in the previous problem. We will plug in delta G naught, R the gas constant, and T for 298 Kelvin, and I get a value of K equal to 8.3 times 10 to the 11th for my equilibrium constant. Once again, a large, well, not so large, but a negative value of delta G naught is consistent with a spontaneous reaction, which gives me a large value of K. Now notice, in this case, we have an exothermic reaction. Delta H naught is negative, which favors spontaneity. But now we have a negative value of the entropy change. Delta S naught is now negative 147 joules per mole Kelvin. Okay, so the question is, what will the equilibrium constant be at a different temperature, namely a higher temperature, 650 Kelvin? So we're going to calculate K at a different temperature and ask ourselves, is that consistent with the signs of delta H naught and delta S naught? We talked about this earlier in the unit. Well, you might be tempted simply to say K equals e to the negative delta G naught over RT, plug in the delta G naught we calculated at the previous temperature, at the previous problem, and then plug in 650 Kelvin for temperature. Don't do it. That's wrong, okay? The delta G naught we calculated in the previous problem, namely negative 68 kilojoules per mole, is a function of temperature. That is the value of delta G naught at 298 Kelvin. At 650 Kelvin, it's going to have a different value, so we're going to either have to calculate the different value, or to make our lives a teeny bit easier, we could simply use the equation, the natural log of K equals negative delta H naught over RT plus delta S naught over R. That gets rid of delta G naught. Actually, it doesn't. Delta G naught is inherent in that, but it shows us exactly how the equilibrium constant depends upon temperature. So I'm going to simplify my life by exponentiating both sides, and I will get K equals E raised to the power of everything on the right-hand side of that equation, which is negative delta H naught over RT plus delta S naught over R. Okay? To plug those in, this is e to the negative 112 kilojoules per mole divided by 8.3145 times 10 to the negative third kilojoules per mole Kelvin times the temperature, which is now 650 Kelvin, plus the standard entropy change, negative 0.147 kilojoules per mole Kelvin over R, 8.3145 times 10 to the negative third kilojoules per mole Kelvin. You will convince yourself that when you cancel units, everything in the exponential term, the units cancel out, which they should, and we get K is equal to e to the 20.72 minus 17.68, or e to the 3.04, or a value of 21. So the equilibrium constant with the reaction at a higher temperature is 21. So the question is this change consistent with the signs of delta H naught and delta S naught? So simply to review, at a temperature of 298 Kelvin, K is equal to, what did I say it was, 8.3 times 10 to the negative 11th? Sorry, positive 11th. Whereas at 650 Kelvin, K is equal to only 21. So as temperature increased, K decreased. Is that consistent? And the answer is yes. Okay? So when the standard enthalpy change, delta H naught, is negative, but the standard entropy change is also negative, as temperature increases, delta G naught increases, the reaction is less spontaneous and K decreases. So yes, for this particular case, the decrease in the equilibrium constant with increasing temperature is completely consistent with the reaction becoming less spontaneous. Now, here's an important question. How do we actually measure the standard enthalpy change and the standard entropy change experimentally? Well, what we can do is create something that's called a Van't Hoff plot. Okay, and let's talk about this. So we have the equation natural log of K equals negative delta H naught over R times 1 over T plus delta S naught over R. Now you may ask yourself, why did he factor out 1 over T and write it in that particular way? That's because you will see that this then becomes of the form y equals mx plus b, where y is the natural log of K, x is reciprocal of temperature. So if we measure the equilibrium constant at a series of temperatures and graph the natural log of K on the y-axis as the reciprocal of T on the x-axis, that predicts that we should get a straight line. Okay? And that straight line then will have a slope of negative delta H naught over R and a y-intercept of delta S naught over R. In this particular type of problem, the slope could either be positive or negative. In the example that I arbitrarily drew, where the line of the Van't Hoff plot has a positive slope, because the positive slope is negative delta H naught over R, that would mean delta H naught would have to be negative, so this would be the case for an exothermic reaction. If you had an endothermic reaction, then the slope would be negative. Okay? So what this lets us do then is a very straightforward experiment. If you can measure the equilibrium constant at a series of temperatures and create a Van't Hoff plot, then you can simply determine delta H naught as being equal to negative R times the slope of the graph, and delta S naught simply being equal to R times the y-intercept of the graph. And let's do an example of that problem to finish up. Okay? So a chemist studied the temperature dependence of this experiment. We see that as the temperature increases, the equilibrium constant decreases. So we're going to determine delta H naught and delta S naught using this reaction. So what we're going to do is to calculate the natural log of K and reciprocal of temperature, and then graph the natural log of the equilibrium constant versus reciprocal temperature to create our Van't Hoff plot. So we open our spreadsheet so that we can easily and quickly calculate the reciprocal of temperature on the x-axis and the natural log of K on the y-axis, and we obtain a lovely straight line. And here is the equation that represents the straight line. Y equals 6,988.71 Kelvin times x minus 21.25. So we will now use those values to calculate the standard enthalpy change and the standard entropy change for this particular reaction. So, as we said before, the slope is equal to negative delta H naught over R, and the y-intercept is equal to delta S naught over R. So, to calculate delta H naught, we will simply take negative times R, 8.3145 times 10 to the negative third kilojoules per mole Kelvin, times the slope, 6,988.7 Kelvin. You'll convince yourself that the unit on the slope is Kelvin, which gives us a value of negative 58.1 kilojoules per mole. Okay? Again, a positive slope here is consistent with an exothermic reaction. And then to calculate the standard entropy change, delta S naught is equal to R times the y-intercept. Because standard entropy changes are normally given in joules per mole Kelvin, I'll use R as 8.3145 joules per mole Kelvin times negative 21.25 to give me a standard entropy change of negative 177 joules per mole Kelvin, the sign being consistent with the fact that we are decreasing the number of moles of gas. So this is how you use a Van't Hoff plot to calculate the standard enthalpy change and the standard entropy change for a chemical reaction. For our final topic in this unit, let's talk about free energy and work very briefly. What is work? Work is defined as force exerted through a distance, And in physics, to calculate the amount of work done, you simply multiply the force exerted by the distance through which it is exerted. Why do we carry out chemical processes? Why do we combust things, for example, and put carbon dioxide in the atmosphere and heat up the planet? Well, because we can get useful work out of the chemical reaction. So the question is, how much useful work can one theoretically obtain from a chemical process? Well, it turns out that the maximum amount of work that you can get from a process is delta G, which, as we saw before, is simply equal to delta G naught plus RT ln Q. So if I have a chemical reaction under a certain set of conditions and I want to know what's the maximum amount of useful work I can get from it, I simply calculate delta G. Now, in reality, in an actual process as opposed to a hypothetical process, the maximum amount of work you can get is going to be less than delta G because no process is 100% efficient. That then is our discussion of thermodynamics. Hope you enjoyed it.